Hi, Alexi from Opto 22 here. Welcome to part 3 of our screencast series showing how to use Opto 22's Intelligent Remote I/O with Allen Bradley Logic Systems. In part 1, we established communications. In part 2, we demonstrated intelligent digital features. In this screencast, I'd like to demonstrate the distributed intelligent analog features in Snap-IO. On the analog side, Snap-IO handles all the features you see here, such as PID loop control, output clamping and ramping, and filter weights. Just as with the discrete features, this functionality is configured and calculated down at the I/O unit level, freeing up the main controller for other tasks. For all the videos, we're using an Allen Bradley 1769 L32E Compact Logix controller, Opto 22 Snap-IO, and a load panel with various inputs and outputs. We'll begin by configuring 2 analog points and scaling both into our desired engineering units. Next, I'll show how we can read the maximum value for the input and set a clamp on the output without any programming in RSLogix. Let's get started. As before, we'll start with the Ethernet IP configurator. I have a few points configured from the previous screencasts, but I want to add the potentiometer. It's wired to module 4, so I'll select that module. The type is an analog input. Scrolling down the module list, you can see there's a wide range of analog signals that Snap-IO can handle. I'm using the Snap AIV, or voltage input, so I'll select that. I'll expand the folder, and the potentiometer that I'm using is connected to the first point, so I'll select that and double-click. I'm going to have the potentiometer simulate a level in a fuel tank, so let's call this point Fuel Level. I selected the module type already, but let's take a quick look at this drop-down box. Here I can change the input range if desired. If I select the Scalable option, I can configure the input to convert to the engineering units and scaling of my choice. I'll click Custom, and now I can type in gallons, which is much more meaningful when dealing with a level in a tank. Now let's scale the input. For the upper and lower values, I can select any 2 known values on my calibration line. For example, let's say I know that when my level reads 0 volts, the tank level is empty or has 0 gallons. I'll enter 0 for the actual lower value and leave it at 0 for the lower scaled value. Now let's say that when my level sensor reads 5 volts, it means there's 100 gallons in the tank. So I'll enter 5 for the actual upper value, and I'll enter 100 for the upper scaled value. I'll click OK, and we're done with that point. Let's configure our display meter next. It's wired to module 2. It's an analog output, and the module part number is the AOV27, or analog output. I'll expand the folder and click on the first point where our meter is wired. The meter will show the level of our tank, so I'll type Fuel Display as the name of the point. Just as we did with the input, we'll go to the module field and select the Scalable option. Let's click on Custom, and again we can enter gallons as our desired scaled units. Now we need to enter 2 data points to set the scaling. Remember, the tank level goes from 0 to 100 gallons. The meter handles 0 to 10 volts DC, and I want it to be able to display the full range of the tank. So I'll enter 0 as the actual lower value, and I'll leave 0 as the scaled lower value. For the upper value, I'll leave the actual high level at 10 volts DC and enter 100 gallons as the upper value. I'll click OK. Notice the true 0 scale value comes from extrapolating my data points down to negative 10 volts DC, which would be equivalent to, well, negative 100 gallons. But what have we done here? 2 things, actually. We've set desired engineering units and scale the values to match the real-world units that we want, all without any programming in RSLogix. All right, now we're ready to move on to creating some assembly instances, so I'll go to the Configure Assemblies tab. I've arbitrarily decided that I will use Assembly Instance 100 for the inputs from the SnapIO to the controller, and Assembly Instance 101 for the outputs from the controller to the SnapIO. I'll select 100 and click Add. If you'd like, you can type a description here. For example, I'll type fuel level input. This can be useful if you have a lot of assemblies. Now we want to read in the fuel level, and that's an analog input point. I'll select point name, and I can choose the point fuel level from the drop-down list. Check out all the options available under Attribute. I could get the value, which would display in counts. Minimum and maximum values are fairly obvious. They are the lowest and highest values recorded by the SnapIO unit since the last time the unit was reset, or since the min and max values were cleared. R value returns the reading in our scaled engineering units of gallons. The next 4 items provide access to the scaling of the input. This means you have the ability to change the scaling on the fly from RSLogix if you were to write to these values. So if a signal starts to drift, for example, you can update the offset or gain. And finally, we have the ability to activate and set the amount of digital filtering, which is useful for smoothing out a noisy or erratic input signal. We'll choose R value and click OK. There are no other inputs wired to the module, so I don't want to fill in the rest of the points on the module. I'll keep the default as no and click OK. Let's add to this assembly instance so that we can view the maximum level reached in our tank. I'll make sure analog input point is selected, and I'll choose my fuel level again. Under Attribute, I'll select a maximum value and click OK. And once again, I'll decline this offer and click OK. This is so much fun, I think we should do another one. I'll click Add. This time, I'm going to select the analog output point because I want to view the value of the fuel meter in RSLogix. I'll choose the fuel display point, and I'll select R value as the attribute. Because this is an analog output point, the options under Attribute are slightly different. For example, we can enable the watchdog timer and also set the fail value if timeout occurs. We demonstrated this watchdog functionality in part 2 of this series. We can also set a high or low clamp on the output, but I'll do that next. For now, I'll keep it at R value and click OK. That takes care of data I want to read from the SnapIO. I'll go to Assembly Instance 101, which I'll use to specify areas that I want to write to the SnapIO from my AB controller. I'll click Add. We want to be able to write to the output fuel display, so I'll select Analog Output Point, and I'll choose the fuel display. I'll select R value and click OK. Finally, we'll add just one more. If you don't want to click on the Add button, you can also double-click right here in this field. I'm going to pick the same point, the fuel display, but this time I'll choose the high clamp attribute. If an output is clamped, attempts to set the output point to a higher value are intercepted by the intelligent I/O and will not succeed. Nothing higher than the high clamp value will be sent to the output. This feature can be useful if, for example, a valve is fully open at 90%. No need to send 100. Or you might want to prevent damage that too high an output might cause. I'll click OK and OK again. Hopefully you get the idea. It's pretty easy, right? Let's check our work by clicking on the Verify tab. In this dialog, we see a summary of our assembly instances. On 100, we have 3 DINTs, or double precision integers. On 101, we have 2 DINTs. I'll click Download, and then Download again to send the configuration to the flash memory of the SnapIO. The download is complete, so I'll click Close. While I'm here, I'll quickly save my work by clicking on the Save icon. Time to go to RSLogix 5000, Rockwell Automation's programming language for their Logix controllers. To keep things simple, I'm going to start from scratch with a new project. I'll go to File, New. Our controller type and software revision number are correct, so I'll type I/O for AB Analog as the project name and click OK. We need to add the Snap I/O unit, so under I/O Configuration, I'll right-click on Ethernet and select New Module. I'll expand the Communications folder and scroll down until I find the generic Ethernet module. I'll name the I/O unit Snap I/O. And because we're working with analog, I'll select Data Real as the COM format. I'll enter the IP address I assigned to my Snap I/O. And now let's look at the connection parameters. We used assembly instance 100 for our inputs, and we had 3 32-bit words. We used assembly instance 101 for our outputs, and we had 2 words. We didn't use the configuration assembly instance, but we need to put something there, so I'll type 102. And we can click OK. Here we could change the requested packet interval time if desired, but for now let's leave it at 10 milliseconds. Let's take a look at the controller tags. I'll expand the inputs so that we can enter descriptions for them. The first element is the fuel level. The second item is the maximum value, so I'll type fuel level max. The last item shows the output, the fuel display. Because this is the input instance, we won't be able to write to the fuel display from here. That's what the output instance will be for. You'll see why we have this field in just a minute. But moving on to the outputs and expanding the folders a bit, let's update these descriptions as well. The first is the fuel display again, but because this is the output instance, we can write to it from here. So I'll name it Fuel Display Write. The second field is the Fuel Display High Clamp. From here, we can set the high clamp value. Although this screencast isn't about programming, I am going to write one little rung of code. I want to move the input value of the fuel level to the output fuel display meter. I'm going to go to the main routine, and I'll add a move instruction to the first rung of code. For the source, I will go to my input instance and select the fuel level. For the destination, I'll go to the output instance and select the fuel display write. Okay, the time has come and we're ready to test our configuration. I'll go to Communications, Download, to download the project to the Allen Bradley CompactLogix controller. I'll click Download, and yes to run it. Let's go over to the hardware and turn the fuel level potentiometer. Notice the fuel display is updating. Cool, it works. Not that we had any doubts, right? Now let's take a look at the tags. I'll open up the folders. Once again, I'll turn the potentiometer. Notice the fuel level, fuel display, and the fuel display write fields all update. Now notice the values. These are in gallons, the engineering units of our choice. No counts here, just the real scaled value, and we didn't need to do any ladder logic magic to do the conversions. Snap I/O took care of all of that for us. Now keep your eye on the fuel level max. If I increase the value of the fuel level, the max value increases. If I lower the fuel level, the maximum value is still captured and retained, again without any programming. Let's do one more thing. I'm going to set a high clamp by entering 75 in the high clamp field. Now I'll turn up the fuel level and keep your eye on the fuel display. Notice that although a higher value is written to the fuel level, as you can see here in the output instance, the value at the I/O point is clamped to 75, as seen here in the input instance. And of course, on the display meter here on the load panel, it's at 75 gallons as well. Thanks for watching part 3 in a 4-part series of videos. We showed you how to configure distributed, intelligent analog functionality such as scaling and setting engineering units for analog points, reading the maximum value of an input, and clamping an analog output. Be sure to visit opto22.com for more information and to watch our other screencasts. See you next time!